Okay, welcome to the Engineering Principles class for September the 17th. Before we start, anybody got any questions you want to talk about? Not hearing anything, not seeing anything. Okay. All right, so up until now, we've been talking about airplanes and why they've crashed. And hopefully you remember that it turns out that the number one reason why airplanes crash is not engineering failure. It's human error, pilot error. But there are still a substantial number of crashes that have occurred due to engineering failures. Now, last time we talked about a variety of different crashes, and in many of them, not all of them, but many of them, there was a common thread, and that's what we're going to be doing for our first real engineering project here. So you may remember that in a couple of the crashes, what happened was that an engine either exploded or maybe the bolt broke and so the engine went flying off. And hopefully you guys remember that airplanes are designed to have safety factors. We call it redundancy. So even though the engine might explode or the engine might actually fall off, that in and of itself should not bring the plane down. Airplanes are designed so they can fly on only one engine. And they're designed so they can fly even when something explodes and shrapnel goes everywhere. But sometimes what happens is that through an incredibly bad stroke of luck, the shrapnel just happens to puncture the hydraulic lines. Okay, the United Airlines case is, I think, the most interesting example there. That was where they had the engine in the tail, and the engine exploded, but should not have been fatal. But the problem was that the shrapnel broke all three of the lines. They actually had not just one backup line, they had two backup lines. There was three separate hydraulic lines. Any one of the lines by itself would have been capable of controlling the flaps and things that they needed. But they routed all three of the hydraulic lines through the exact same spot in the tail. And when the engine exploded, the shrapnel just happened to hit that one spot, took out all three lines. And so now the plane is now unflyable, not because of the loss of the engine, but because of the loss of the hydraulics. Okay, so what we are going to do for our first real unit here, when I say real, because the paper airplane thing didn't count. We are going to talk about hydraulics and pneumatics. That is something that is extremely important for aeronautical engineers. But it turns out that even if you're not an aeronautical engineer, even if you're a mechanical engineer or some other field, hydraulics is something that you need to know a lot about. Okay, so let's talk a little bit about hydraulics. So what you see on the screen right now are various parts of an airplane. And so let's just pick one here. So the rudder, okay, that's this piece right here. And so what happens is the pilots way up here in the cockpit, they have a foot pedal, and they can push this foot pedal, and that will move the rudder either to the right or to the left to help steer the airplane. And there are also these things here called ailerons, and they have them on both sides. It's only labeled on one, but it's actually in both. And so that's connected to the steering mechanism. On some airplanes, it's kind of like a steering wheel. They call it a yoke, but it's pretty much like the steering wheel on a car. And so on Boeing aircraft, they use that. But on the Airbus airplanes, they use like a joystick controller. But either way, okay. So there are hydraulic lines that run back here, and so let's say it's a Boeing because that's the easiest to understand. So when they pull back on the yoke, which is, remember, kind of like the steering wheel, what happens is the ailerons go up, okay? And then when they push forward on it, the ailerons go down, and that will steer the plane to where the plane will either go up or down, depending on that. Okay, and you can see that there are all sorts of other things. They have flaps in the back that are called elevators. They have flaps right here that are called spoilers. And what that is when the plane is coming in for a landing. Basically, anytime the plane is moving really slowly, they need to make the surface area of the wing bigger because you need more lift when the plane is traveling more slowly. So during takeoff and landing, they put out these flaps to make the plane bigger. And then these spoilers are things that they use when they're coming in for a landing and they want to slow the airplane down. Then the spoilers slip up. But all of these things that you see here, all of these are controlled by hydraulics. Okay, so let me go on to the next page here. What you see here, here you can see both the spoilers and also the flaps. If I can get my annotation to work here. All right. All right. So what you see here, these are flaps. These are things that normally go up inside the wing. When I say normally, I mean when the airplane is up high in the air traveling at high speed, these flaps, they go up inside the wing because you don't need all of that wing surface area when the plane's traveling at high speed. And so you don't want the extra resistance that it brings. And then when the plane is coming in for a landing or when it's taking off, when it's traveling more slowly, the flaps come out. Now, in this case, not only have the flaps come out, but they've also tilted downwards because we're trying to slow the plane down. The airplane has now landed and we're trying to slow the plane down. So the flaps come out and then they go down. And then these things are called spoilers, so they go up. So we're trying to get as much resistance as possible to slow the airplane down. But the reason that I like this picture so much is because inside you can see, let me switch to a different color. You see the hoses and pipes. So inside here, there are pipes and hoses running all over the place. Okay, those are hydraulic lines. Those are the things that make the flaps come up or go down. They're all based on hydraulics. So what we are going to do for the next little while is we're going to learn about hydraulics and how they work. And there's also something called pneumatics, which is very similar to hydraulics. So if you've learned the one, then you've basically also learned the other. So before I go on, let me just ask a question. I'm sure that there's somebody here who can tell. What is the difference between hydraulics and pneumatics? So how are they different? And also while you're at it, how are they similar? I'm willing to bet there's somebody here that can answer that question. Come on, don't make me lose my bet. What are hydraulics? What are pneumatics? How are they similar? How are they different? All right. All right. So Marshall is saying that hydraulics use water and pneumatics use pressurized air. Okay, very good. Yeah. So let me just modify the wording slightly. Hydraulics use liquid. Now, water certainly could work. They could use water if they wanted to. But quite often they don't use water. And there actually is a very good reason why they don't. Can anybody think of a reason why you would not want to use water in your hydraulic system?
Would it evaporate if it gets too hot?
Well, it's entirely enclosed so that even if it did turn to water vapor, it couldn't escape anymore. Yeah. Okay. So Marshall and Preston and Don's Marshall and Preston are saying because it can freeze. Don's is saying because it rusts. Now, water doesn't actually rust, but water can cause the metal to rust. Okay. But really, it's the freezing that's the big thing. You guys know that when water freezes, it expands. And so if you have a bunch of lines that have liquid in them, if that liquid is water, then in the wintertime when it gets cold at night, if that water were to expand, it would break the system. Okay, so hydraulics could in theory use water, but they pretty much always use a special kind of oil instead. They call it hydraulic fluid. Um, okay, so let's look at a couple examples here. Okay. All right, just more things on airplanes that use hydraulics. I got a lot of pictures. We could talk forever. You see how the hydraulic lines they run through the airplane here. A lot of people are surprised when they realize how much the airplanes rely on hydraulics. Okay, so here is a great example of how hydraulics work. Let's say that you have a piston. And so what you're seeing right here, okay, this is the outer shell of the piston, and this piece right here is a movable thing that can slide in and out. Okay, so this is actually the piston itself. This part out here is the piston housing, and you can see that there are two openings. One opening right here. So let me switch to a different stroke. Okay, so if we have a pump and we push fluid into this part of the piston at really high pressure, what's going to happen is it's going to push the piston so that the piston will move out. And so what we can do is we can take this end of the piston here and we can connect that onto some airplane piece. You know, let's say here's the pivot point and here's the piece right there. So when the piston goes out, it makes the piece move up, and when the piston comes in, it makes the piece move down. And you can get a lot of force with these things, right? So this then can make the piston go out. And now let's suppose that the piston is now in the out position and we want the piston to come back in now. All right, well, that's no problem. All we have to do is just change it so that now we push the pressurized fluid in from the right side rather than the left side. And that's actually shown down at the bottom here. Let me use the picture down at the bottom because that's what they intended here. Okay, so what we're doing now is we're changing it so that this pressurized fluid now is coming in from the right side. And so that's putting a whole lot of force here. So now the piston is now going to move in rather than coming out. And these are hydraulic pistons, but it doesn't have to be hydraulics. Whatever the fluid is that's coming in here, it could be liquid, but it also could be air. Air works just, air works perfectly well. So you could just put high pressure air here to make it go out, and or you put high pressure in here to make it go in. So if we're using a liquid in order to do this, then we call it hydraulics. If we're using air to do it, then we call it pneumatics. And notice there's a P at the beginning of pneumatics. It's a silent P, but make sure you put it in there when you spell it. Okay, so now let me ask the question, why would we want to use liquid sometimes and air other times? What advantage might we have in using liquid, or what advantage might we have in using air? I need somebody to respond here. I know that some of you know the answer.
Do hydraulics push harder or like have a harder force than pneumatics? Because I mean, air can has a certain strength to a certain point, and I mean, liquids, I don't know. I guess they have more strength.
Okay, that's a really important question. What do you guys think? Do you think that liquids can push harder than air can? So I want you to type into the chat box. If you think that yes, liquids can push harder than air, I want you to type yes. If you think no, I want you to type no. Okay, it looks like everybody is in agreement that liquids can, everybody except for one. Okay, Presley is not convinced. Presley, can you unmute yourself and tell us why do you disagree with that?
Let's see, is this working?
Yeah, I can hear you.
Okay, my internet went out. I don't see any real reason that it would be any stronger. There, I mean, all matter still takes up space, so as long as you have enough of either, it should work the same.
Okay, I'm going to agree with Presley on that. The total amount of pressure is determined by how strong your pump is, and the pump can push just as hard on liquid as it can on air. So it's not necessarily, in fact, it is not the case that you can get more force out of hydraulics than you can out of pneumatics. But there is another really important difference that turns out to be very, very relevant to what we're talking about here. So liquid is non-compressible. That does not mean that you can't push on it. That means that when you push on it, it doesn't change volume. Whereas air is very different. Let me stop sharing here. Okay, so if I have a balloon filled with air, if I can wrap my fingers totally around the balloon and I squeeze the balloon, what's going to happen is I can make that balloon smaller. Now it's going to want to try and sneak out in between my fingers, so I'll have to make sure that doesn't happen. But I can take what is 1 gallon of air, and if I do it right, I can press it down and I can change that 1 gallon of air into a half a gallon of air. Now that half a gallon of air is going to have a lot higher pressure than the 1 gallon did, but I can compress it. Whereas if I tried that with liquid, if I take a gallon of liquid and I squeeze it, I can't change the volume. I mean, 1 gallon of liquid is going to be 1 gallon of liquid, no matter how much pressure I put on it, it does not change volume, whereas air does. Now, that turns out to be very, very, very important when you're using pneumatics. So let's suppose that I want to move the piston out. Whoops, sorry. I need to remember to turn on annotation before I touch my screen. Let's say I want to move the piston out, but I only want to move it out a little tiny bit. So let's say I only want to move it out maybe just 1 inch. Okay. Now, if I use pneumatics, I can put in exactly the right amount of liquid that, I can calculate how much volume of liquid I need to put in here in order to make it move 1 inch. I put in that much liquid and that thing will move exactly 1 inch, no more, no less. Very, very controllable. But if instead of using liquid, I use air, okay, so I'm not using hydraulics anymore, I'm using pneumatics now. Okay, air can change volume depending on how much pressure it feels. So if I put a bunch of air in here, the volume of that air will change depending on whether it's feeling more pressure or less pressure. And so if I want that thing to move exactly 1 inch, I got a problem if I'm using pneumatics. Like, it's very difficult, if not impossible, to get that cylinder to move exactly the right amount if I'm using pneumatics. Whereas with hydraulics, I can get it exactly where I want. Now, air does have an advantage, okay? The advantage is this. Let's suppose that instead of wanting to move the piston out by a tiny amount, let's say I don't want to do that. What I want to do is I want that piston to come slamming out as fast as possible, because I want to use it maybe to, let's say I've got let's say I'm designing a robot and I want that robot to shoot a ball through some hoop that's really far away, which, by the way, is not hypothetical. You guys know that Ames is a member of an international robot league called First Robotics. And every year the challenge changes a little bit. And some years the challenge has been to shoot a ball through the air. And so one of the ways that many teams chose to do that is by using pneumatics. And so the really nice thing is you can have a high pressure tank right here. Okay, so this is a very high pressure air tank. All right, and you've got a valve right here. Okay. So what you've got is you pressurize this baby to really high air pressure. Okay, but it can't get out because you've got this valve right there. When you're ready to shoot the ball, what you do is you open up the valve. Oops, I pushed the wrong thing there. Okay, so when you open up the valve, all of the air can come rushing in pretty much instantaneously. And this piston goes from being fully closed to being fully open, okay, in no time flat. This piston comes shooting out there. In fact, it comes shooting out with so much force that you could easily kill somebody using this piston if you're not careful. Have any of you seen the movie called No Country for Old Men, I think is the name of it? There's the bad guy in that movie. He kills people by walking around with a high pressure tank of either air or nitrogen and a piston like this, and they're connected together. So he holds the piston up next to somebody's head, opens up the valve, and that thing comes out like a bullet, and he kills people that way. So if you tried to do that with hydraulics, you would not be able to do that, because with hydraulics, as soon as you open this valve here, the liquid comes flowing in, but as soon as a little bit of liquid comes out, you've now lost all your pressure. Let's say you have a super high pressure tank there with all sorts of, with liquid in there under tremendous pressure. As soon as you open up that valve and just a few drops of liquid come out, you've lost all your pressure. That's it. So the piston will move a tiny little bit and then it'll stop because of the fact that liquid is not compressible. So if you want to move the piston, you can't use a high pressure tank of liquid. What you have to do is you have to have a pump, and you just continually pump the liquid in there, and it takes time to do that. So this piston is going to move much, much more slowly, very repeatably, but very slowly. All right, so pneumatics are great when you want that piston to come slamming out fast. If you want that piston to be more controlled, then pneumatics are a lousy way to do it. Then what you need is hydraulics. So on an airplane, they pretty much never need the thing to come slamming out. On an airplane, you need to have fine control. So on an airplane, they're going to use hydraulics. We could, in theory, use hydraulics in this class too, but we don't for a couple of reasons. One big reason why we don't use hydraulics is because it's more expensive to have all the pumps and things that you need to pump the fluid. And also, actually, probably the bigger reason why we don't use hydraulics is because if you get a little bit of a leak and hydraulic fluid comes out, it gets everywhere, and boy, it's a mess to clean up. Oh boy, is it ever a mess to clean up. Whereas if you use pneumatics, then if you get a little bit of a leak, no problem. You don't have to worry about cleaning it up. So in this class, we make things using pistons and whatnot, like what you saw before. And the neat thing is that these pistons that we're talking about here, they can work just as well whether you use them on hydraulics or whether you use them on pneumatics. Here is a picture of a piston, and this is one that we use in our robotics club. The name they use here, the Bimba, that's just the company name. That's all it is. I mean, these guys can be made by a whole bunch of different companies. But there's a fitting right here. And so if we send in high pressure air, that makes this piston come out. And then if we want to retract it, then we change the air. So instead of going there, it comes in here. And that makes the piston come in. And so this is the kind of piston that we use at Ames. And this piston works equally well, whether it's being powered by air or whether it's being powered by a liquid. The piston doesn't care. It works just as well either way. All right, so this is what we are going to be using, or at least let me rephrase that. This is what we would be using if we were meeting in person at school. Okay, so right now we're running into a problem because we're meeting online. We can design pneumatic systems, but I'm thinking that most of you don't have the equipment at your home that is needed in order to actually build a pneumatic system. So what we're going to do for the next couple class sessions is we're going to design a pneumatic system. We're going to do the drawings. We're going to figure out the theory. We're going to make it so that we know how to build it. But then we're going to have to stop there because at your homes, you don't have all the equipment. Now, I'm hoping that the coronavirus problem does not go on all year long, all school year long. I'm hoping that at some point we'll be back at Ames, and then we're going to have our designs all ready to go. So then what we can do is that we can then build a system, because I have all the components. I have lots of cylinders. I have lots of tubing. I have lots of valves. I have lots of air compressors. I have everything we need, but I have it at school, not at home. All right. So what we're going to do is we're going to design a system. All right. So let's talk about the system that we need to design. Let's do some, so let's start with a functional specification. And that's going to be your homework tonight. We're going to do this the same way that we did with the airplane, the paper airplane. So I'm going to pretend that I'm the customer, and you are going to pretend that you are the engineer, and you are a member of a very large engineering team. You've got 20, 30 different engineers on your team. But when you meet with the customer, you don't want all 20 or 30 engineers to meet with them. The customer is going to feel overwhelmed and be very uncomfortable. So the team has to send one representative to meet with the customer. You are that representative. I am the customer. So I'm going to verbally explain to you what I want your engineering team to do. You have to take careful notes about everything that I tell you. If I accidentally forget to tell you a couple things that you think you might need to know, it's your job to ask questions to pull the information out of me. All right. Then after you and I meet, you then are going to go back to your engineering team, and you are going to present them with a document that describes what the customer wants. Can you guys type into the chat box, what do we call that document? Really important that you know. Come on, I know that some of you know. I know that all of you know. Somebody type in the chat box. What do we call the document? It's not an engineering specification. It's a functional specification, right? So Dylan, I want you to tell me what's the difference between, because I'd like you to unmute yourself and tell me verbally, what's the difference between an engineering specification and a functional specification? So Dylan, do you
The-
have a mic? Okay, go
Yeah,
ahead.
the difference between an engineering specification and a functional specification is the engineering one is where you like put how you did it, kind of
How you intend to do it.
like yeah, how you intend to do it, and stuff like that. You put drawings of how you intend to do it and everything, and so. But the functional specification, you're identifying what the problem is, basically.
Okay. And there's one very important thing that the functional specification must not do. How about Ryan? What is the thing that the functional specification must not do?
Isn't it tell you how to build it?
Okay, you're saying that's what it should not do, right?
Yeah.
Okay, very good. Yes, the functional specification should describe what is the job that needs to be done without giving any hint as to how you plan to do that job. Okay, so that's really important. So what we're going to do right now is we are going to meet where you and I are going to talk, and we're going to pretend that it's one-on-one, even though it clearly isn't. And so I'm from an airplane manufacturer. I work for Boeing. Okay, and I have a job that I'm thinking of hiring your company to do for me. And so we're going to describe that job. And when we're done, you are going to write up a functional specification that describes the job that needs to be done without giving any hint as to how you intend to do the job, right? Okay, so if we're ready, okay, so let me take off my teacher hat and put on my customer hat. All right. Okay, well, thank you very much for coming to Boeing here to meet with us today. We're really hoping that you and your company can help us solve this problem. I'm going to go ahead and start describing the problem right now that we want you to solve for us. And then I'd like you and your engineering team to come back with a proposed solution to the problem. Okay. All right. So let me open up a screen here. And okay. All right. So here's the problem. We are designing an airplane here at Boeing, and we actually, let me go back to this one. Okay. Okay. So we're working on the tail of our airplane, and we've got this rudder here. It's a piece that we want it to be able to turn to this side sometimes and turn to that side sometimes. It's a really big piece. Now, when the airplane is flying, there's a lot of pressure there. So when this rudder comes out here, there's a whole lot of air pressure pushing on it. So we need something that can push this thing with a lot of force. But it has to be very, very controlled. When the rudder comes out, we need to have superfine control. So if the pilot decides that he wants the rudder to only come out 1/2 of an inch, then by golly, that rudder had only better come out 1/2 of an inch. Okay. Or if he wants it to come out maybe more, say he wants it to come out 3 inches. Okay. 3 inches. Then by golly, it better come out exactly 3 inches. Now, it's not really essential that when the rudder comes out, it doesn't have to come out instantly. I mean, if it takes it a second or two to come out, we're okay with that. But it's extremely important that it comes out only the amount that we want it to come out. Okay? So we need you guys to design us a system that that can push the rudder out a certain amount. And we need it so that if the pilot commands the rudder to come out, it'll come out. But then also if the pilot commands the rudder to come in, the rudder needs to come in. So the pilot needs to be able to control it both ways. Now, we've thought long and hard about whether it's better to use hydraulics or pneumatics, but I'd like to hear your thought on the matter. So can you tell me which would you recommend we use for this application? Do you think hydraulics would be better, or do you think pneumatics would be better? And I need one of you.
Hydraulics?
I think hydraulics would be better since it'll be more precise, and since you don't really need like instant movement. Yeah.
Okay, good. Yeah, I agree with you, and I see that those of you that typed in the chat box agree. Okay, so clearly what we want is hydraulics, not pneumatics. Okay. All right, so what I want you to do is I want you to design a system. Now we'll handle the actual rudder itself. You don't need to design the rudder. You just need to design the thing that moves the rudder. So let me switch to a whiteboard here. Okay, so what we need from you is some sort of a mechanism, okay, that has a piston that connects to something. So we'll take it from here. Okay. So the rudder part here, okay, rudder, we'll do the rudder. So you don't need to worry about that. What we want you to do is we want you to do this, the piston here. And we also want you to do the stuff that drives it. So somehow, and I'm going to leave this up to you, we need to have some sort of a mechanism that can push the fluid in here. And sometimes it's going to go in this side and other times it's going to go in this side. Because remember, inside the mechanism here, we have this piston, okay? So we need you to somehow figure out the piping system so that when the pilot flips the switch one way, the piston goes out. When the pilot flips the switch the other way, the piston goes in. And then we're figure this is your area of expertise, is to do all that. So I'm not going to try to suggest to you a way to do that, but we need you to come up with a solution for that. Okay, so do you have any questions?
So do you want the rudder to turn left to right, or do you want the rudder to come out like 3 inches, as you were saying, 1.5 inches?
Okay, I'm glad you asked that question. That's something that we will worry about, okay? We are designing the rudder. We're not asking you to design the rudder. We're just asking you to design the thing that pushes the rudder. So whether it pushes to the right or to the left, or whether it pushes up or pushes down, that's not for you guys to worry about. We'll take care of that. You just need to design something that pushes the piston out when we want it to go out and brings the piston back when we want it to bring back. Any other questions? Go ahead.
Do we need to worry about like how big our design is, that like so it fits?
Yes, yes. You definitely need to worry about how big it is. I'm glad that you mentioned that. I accidentally, forgot to talk about that. Yeah, let's talk about the force that's required, okay? So, like I said, when the airplane is flying and this rudder gets pushed one way or the other, okay, that can take a tremendous amount of force. So we have calculated that the amount of force needed by your device could be as much as 1,500 pounds of force, okay? So whatever device you come up with, it needs to be able to push with as much as 1,500 pounds of force. And also, by the way, when it retracts, when it comes back in, it might also need to have 1,500 pounds of force when it retracts as well. So the size of the piston, well, we'll leave that up to you to decide. But I'm hoping that you guys realize that with pistons, the bigger the diameter of the piston, the more force you're going to have when it pushes it out. So I'm going to leave that up to you guys. You guys are the experts on this, not me. You know, we design airplanes. We don't design hydraulic systems. We just use hydraulic systems. Okay, so it's up to you to decide how big of a piston you need, based on the requirement that it has to be 1,500 pounds of force. Any other questions? No other questions?
What materials do the pipes need to be made out of, or the
Ah,
piston?
yes, I can see how that would be an important piece of information to know. All right. We want it to be strong, but we also want it to be lightweight. So titanium is really, really good at being strong and relatively lightweight. Now, if this was really, truly an airplane, we might want it to be made out of titanium, but actually, let's just say aluminum is good enough. And by the way, I'm going to take off my customer hat, put on my teacher hat. The cylinders that we have at Ames, those are all made of aluminum. It turns out that aluminum is strong enough, and it's also really light and easy to work with. So if you make them out of aluminum, that would be acceptable to me. Other questions?
You want this design to be cheap, or do we have like a limited budget?
Well, normally price would be an issue. But in this case, I think you've got enough things to worry about without having to worry about price. So I'm going to say, yeah, don't worry about cost. Okay. Just focus on making it do the right job. But I'm glad you asked that question, because that is a very important question most of the time.
Are we allowed to do research on other planes?
Yes, absolutely. You are encouraged to do research. But remember, you don't have to design the airplane. You don't have to design the rudder. That's our job. You just need to design the hydraulic system. So when you're doing research, I would recommend that you don't bother researching how airplanes work. I would focus your research on how do hydraulic pistons work, okay? How do hydraulic pistons work? That's what you want to research. Okay, so I see Moses is asking, how long can the pipe be? Thank you for asking that. That is an extremely important question. And it's one that I accidentally, wink, forgot to mention. So I'm glad that you caught it. Okay, what I need the piston to be able to move a certain distance. And if the piston can't move that distance, it's not going to do the job for me. So in our application, it turns out it doesn't need to move very far. If it moves 9 inches, that will be acceptable. Okay, so when the pilot issues the command for the thing to come out, the piston needs to come out at 9 inches, and then when it comes back in, it goes back in. So thank you for asking that question, Moses. That is a very important one. Other questions? Not hearing anything, not seeing anything. Okay, now possibly one reason why you're not asking questions is because you don't know enough about hydraulics to know what questions to ask. That actually is the case a lot. So let me help you out here. Let's get our whiteboard out, and let's clear out all this other stuff. Okay, so I'm going to stop being the customer for just a minute. I'm going to go back to being the teacher again. Okay. I'm hoping that by now you guys have a good feel for how pistons work. Okay, so what I'm going to draw first is the piston chamber. Okay, so there's the piston chamber. Okay, and actually, I probably should have drawn that a little differently. Let's try that again. Okay. Okay. All right. So that's the piston chamber. And so now I'm going to draw the piston itself. So here's the piston itself. Okay. All right. And we'll switch to a different color still. Okay. So what we're going to, haven't used green yet. Okay. So hopefully you guys understand that when you push the liquid in here, okay, then what's going to happen is you're going to have a whole bunch of pressure in here, and it's going to push the cylinder out. But other times you want the cylinder to come, or you want the piston to come back in, right? So then what we need to do is we need to get rid of the pressure here, and we need to instead to send in the liquid through here. Okay, so here is the thing that is going to be the trickiest part of the job for you. You are going to have to figure out a way to have a pump. So this is going to be an oil pump. And you need to figure out so that depending on how we go with various valves, okay, so we're going to have a whole bunch of valves and things in here. And we're going to make it so that sometimes it makes the fluid come in this way, and other times it makes the fluid come in this way. And so you have to design how you're going to do the piping and how you're going to work the valves in order to make this happen. This right here, this is the tricky part. The cylinder, you don't have to design a cylinder. You can buy cylinders off the shelf. And so what now, you do have to get the right size cylinder, because remember, Moses was asking how much does it come out? So it has to be at least 9 inches of travel. That's really important. And then the other thing that you needed to know is that the total force here must be at least 1,500 pounds. Okay, so you're going to have to do a little bit of math here in order to figure out how much pressure does this pump have to be able to provide. And together with that, you're also going to have to figure out what is the diameter of this piston. Okay, because if you use a really, really, really big piston, then you don't need such high pressure. Just a moderate pressure can give you a large force if you have a really, really big diameter piston. But a really, really big diameter piston may not be desirable for lots of reasons. Maybe it would be better to go with a smaller diameter piston. And if that's the case, then you're going to need a pump that can put out a higher amount of pressure. So what you need to do is you need to figure out what's the relationship between pressure and diameter of the piston to give you the amount of force that you need. I don't want to give that away. That's one of the things that you're going to have to do some research on. So you can see you've got a bunch of things that you need to think about here. But that's part of the engineering specification, which is not tonight's homework. Tonight's homework is only the functional specification. So although you are going to have to think about this at some point in the near future, not tonight. You don't have to worry about it tonight. Your job tonight is just to make a functional specification describing the problem. Okay? All right. So do you guys think that you know enough that you could now write up a functional specification? So give me a yes or a no in the chat box or thumbs up or whatever. So yes means that you think you now have enough information that you can write up a functional specification. No means that you don't. Okay, good. Now, one other thing, hang on just a sec while I grab something. Okay. If you're hearing some background noise right now, I apologize. Some people are cutting the lawn right outside the window there, so it's kind of a little bit noisy. Okay, so in addition to writing up the functional spec, I want you to start doing some research on how you might possibly meet the need here. And let me suggest something that will be a great resource for you. Your textbook. Up until now, we haven't used your textbook. Well, it's going to come in handy right now. In your textbook, they have several different chapters. Some of them talk about electrical things, some of them talk about mechanical things, some of them talk about computer-related things. There is an entire chapter of your textbook that is devoted to what's called fluid power, which is another way of saying hydraulics and pneumatics. So if you get out your textbook and you turn to chapter 7 in your book, okay, what you're going to see is that they talk all about fluid power and how it works. They talk about different valves that you might want to use to make the hydraulic systems go various ways. They talk here about pistons. They've got a really good picture right here showing how a piston works. And they talk about dual action pistons, which is the kind that we want. And up here, they talk about single action pistons, which is another kind that I'm not going to take the time to talk about. They talk about different types of fittings that you might want to use. So this chapter here, chapter 7, is really it's an excellent resource. So what I would suggest, now I'm not going to require that you read the whole chapter 7, but I want you to look through it and make notes about the things that you find in there. And what you're going to find when you read chapter 7 is that they also give you some information that will help you calculate how much force a piston can produce depending on the pressure. So there's some mathematics involved here, and they do a good job of describing it in the book, where they give you formulas. So if you know the pressure and you know the area of the piston, you can calculate how much force that piston is going to have when it goes out and when it comes in. So I don't want to spoil it by reading the book for you. I mean, you guys are big girls and boys. You can do the reading on your own. So you only have one deliverable. Next time we meet, which by the way will be Monday. So on Monday, I need you to turn in a functional specification, but I would also like you to have started reading chapter 7. You don't have to read the whole thing. You know, just skim through and find out the important stuff that's related to what we need, and start coming up with some ideas. Because what we're going to do on Monday is we're going to do some brainstorming. I'm going to break you up into what Zoom calls breakout rooms. And so you're going to work together in small groups and you're going to do some brainstorming. But that's going to be on Monday, because you can't do the brainstorming until you first do the functional spec. So that's your homework tonight, is do a functional spec. Okay, so I think we've covered everything that we need to for today. Do you guys have any questions? Is there anything more that you need in order to understand what the job is that needs to be done today? Okay, so no questions. All right, good.
Oh, I have a question, but it's just on one of my own assignments.
Okay, so let's talk one-on-one about that afterwards. All right, so Marshall is asking whether or not there's an online textbook. I am not aware of any online textbooks. Now, it's entirely possible that there is. I mean, there's a lot of pirate copies floating around. Like, if you guys probably know more about how to get on pirate copies of music and books and stuff like that. You probably know more about that than I do. But you guys should all have a real textbook. You shouldn't need an online textbook. Every single one of you should have a real textbook. Okay, so before you guys leave, remember to type "bye" into the text box, into the chat box, because otherwise you won't get credit for being here the whole time. So goodbye to all of you guys. functional SNI. Okay, and if any of you want to stick around and talk about old homework assignments or anything else, that's okay, I'll do that. And here what I'll do is I'll turn off the recording so that we can talk without the pressure of knowing that everything we say is being recorded.